All right, Foundations Pre-Cal 10. Here is a short video on simplifying radicals and then entire radicals into one big radical. So going from simplified back into entire. So full E lesson is available, but here's a short. So remember that when we're simplifying a radical, we are looking for either two perfect square factors. So we can kind of do this two different ways. We're looking for a perfect square factor, or we're looking for two identical factors under the radical. So I'll show you both here. For 44, I'm going to think, can I factor out 44 so that one of those factors is a perfect square? And I can, because root 44 would be the same as root 4 times root 11, which I can write as root 4 times root 11. And then I can simplify the root 4 because it just equals 2 to root 11. So that is simplified. Now, the second way would be to break that number down. So again, it comes back to, you can use your factor tree. So 80 is 8 times 10, 8 is 2 times 4, 4 is 2 times 2, and then 10 is 2 times 5. So that means under my radical, I essentially have 2 times 2 times 2 times 2 times 5. And what you're looking for is every time you see two identical factors, right, because it's a square root, they come out as 1. So that's going to happen here twice. And we have the 5 left on the inside. So we're left with 4 root 5. So two different ways to do that. So let's look at two more examples. So we'll do same, show you both ways here. So the first one is breaking it down into factors. 500 is 5 times 100, which is root 5 times root 100, which root 100 is 10. So we get 10 root 5. For 375, I'll do it differently. We'll break it down using a tree. So divide by 5, goes in 7 times with 2 remainders, so 75. Divide by 5, and I get 15, and then I get 3 times 5. So that gives me 3 times 5 times 5 times 5. So again, every time I see two identical factors, they'll come out as 1, and I'm left with 5 root 15. So you can see that we're going from a complete, or what we call an entire radical, into a simplified radical. And it's a matter of identifying perfect square factors or finding two identical factors underneath the radical. So it's the same process when you consider cubes, except now, guess what? We're looking for perfect cube factors, or three identical factors. So if we look at 24, well, that's cube root of 8 times the cube root of 3, and I use that one because I know that the cube root of 8 is a perfect cube, so I get 2 cube root 3. So that's by identifying perfect cube factors. The other one will be to break down and find three identicals. So we'll take 192, divide by 2, 96, divide by 2, 48, divide by 2, 24. Now you could already just go, well, there's 3, so I know a 2 is coming out, and keep working with 24. Well, 24 is 4 times 6, which is 2 times 2, 2 times 3, and again, look, 3 more 2's, so another 2 is coming out, and what's staying in? Well, my only factor that I have left, this 3. So you could break it down that way too. Again, this is more than just procedure. It's about understanding what's happening, and you'll find there's a number of different ways to look at it. So entire radicals, when we go back in, and there's an interesting piece that's going to happen on this one and this one that I'll talk about in just a second. So we'll do the first one first, 2 root 5. So you just got to think, one, it's a square root, and if a 2 came out, that means I must have had how many of them on the inside? 2 of them. So you just put them back in as however many there were. You could also think, transform this back into its perfect squared under a root. So 2 is the same as root 4. So you could write it like that, which then gets you back to root 20. So either way you do it, but just think, when you go back in, you need 2 of them, because when you're coming out, you had 2 of them. Now for the negative 3 root 11, we have an issue here. This negative does not mean negative 3. Okay, this means negative 1 times 3. Anytime you see a negative, technically that's what you see. And that matters here for a square root because you cannot take the square root of a negative number, right? Because what is a square root? It's the same number times itself. And 2 times 2 is 4, and negative 2 times negative 2 is 4. There's no way to get a negative square root, which means a negative can never exist inside the root, so the negative could never come out of the root. So what that means is on a square root or an even indexed root, that negative stays where it is. So the negative does not go back in, but then we get 3 times 3 times 11, which is negative 99. So that's a pretty important caveat there. Because on a cube root, negative 1 times negative 1 times negative 1 is negative 1. So if you have a cube root or a fifth root, basically if you have an odd powered or odd indexed root, the negative can go back in. So in this case, you can keep the negative with the 2. So you can consider that it's negative 2, negative 2, negative 2, because that's just a 2 3 times and a negative 1 3 times, and then times 2. So you will have here the cube root of negative 16. You are allowed negatives in a cube root or a fifth root, but you are not allowed negatives in a square or an even indexed root. It's going to come in handy in grade 11, so I figure why not have a look at it now. Okay, great work. Keep it up. Keep looking for shorts. We're going to be moving into relations functions and one-to-one functions after this. So we'll move away from exponents and radicals for a little bit, but you're lighting it up. Good job.